Hi everyone, welcome to the first of many sessions of the Mathspace Academy. My name's Andrew and I'm the head of content here at Mathspace. My team and I are responsible for every question, lesson, image, applet, video, anything that you interact with in Mathspace is written by my team and I. We are all really big believers in maths education. We're definitely the super nerdy teachers, and we want to try and bring every subject to life in Mathspace. We also read all your feedback. If you've ever sent feedback to Mathspace, we read every single piece of feedback we send, or that you send us. This particular course, I'll also mention, targets the New South Wales curriculum. If you do happen to be out of New South Wales in a different state, then everything I talk about today is still going to be relevant for you in a different state. But this particular course may at times start covering things that are not relevant for your state, and we'll let you know well in advance if that's going to happen. Everything I'm about to show you is going to make a lot more sense if you're logged into Mathspace. If you don't have a Mathspace login, ask your teacher, and I'll show you around the student experience in just a second. Everything I say today is going to get recorded. I've got the URL up there on the screen. Mathspace.co/academy will be where you can access all the recordings of all the classes. The Zoom chat, that's for you and everyone in the audience. I do have it open here. I'm just going to let it scroll by. I'm not going to be paying a lot of attention to it. If you do want to chat, go ahead and do so. But if you actually want to ask a question of me that I might be able to answer, then use the Q&A feature. At the bottom of the screen that you can see my face and the screen on, there'll be two little bubbles. If you click on Q&A, you can ask me a question and I can then answer it for everybody else. So if you have any questions about anything that I show today, or things about Mathspace in general, then open up that Q&A feature and I will address everybody else. And I'll try and leave some time at the end to make sure everybody's questions can get answered. So without further ado, what are we going to be covering today? Well, first of all, I'm going to show you my student account. David Bowie dinosaur avatar, best avatar. This is my student account. So here I've got my dashboard. This is where I do tasks and look at my shares and recommendations and everything else. I'm actually going to look today start by looking at the topics page. Today, I'm going to be covering the networks section as much as I can get through in a single hour. So it'll be a bit of a fast-paced overview so you can see what Mathspace has to offer. And if you want to brush up on any of your networks skills, where you can find things. So first of all, if you're in your own Mathspace account and you click on topics, make sure that it says New South Wales Maths Standard 2 Year 12 or whatever the equivalent is in your state. Should be the Year 12 textbook selected, otherwise it won't make sense. Now, for other states, it might not be number 9, but for New South Wales, number 9 is the networks topic. The thing about the topics page is that it lets you track your progress. Each of these subtopics are full of questions that you can do and master yourself. So if I open up something like degree in adjacency 9.03, not only can I view all the questions, I can also view the lesson, and I'll be showing some lessons today. And if I'm ready, I can jump in and practice, and I can start charging up my mastery here. Once you have all of these mastery bars all filled up, you've mastered the topic. And then this bar over here on the left will also get filled up. So maybe you've already been using Mathspace a lot. Maybe you've already done a bunch of networks. You'll find that there's some green bars here. You know what? I'm just going to jump in and have a go at one of these just to show you. Most of today won't actually be going into Mathspace. I just want to show you how you can use Mathspace to check that you understand all the things that you're going to need to understand before your final exams. So let's just jump in, practice, let's go. We're going to be loading up a question. There'll be a thing about what's new. There, we'll get used to it. Okay, first question that comes up. Which of the following are valid networks? Select all that apply. What is a network? Well, a network is kind of the easiest thing that you've ever encountered in maths, in my opinion. The nice thing about networks is that you don't really have to know any maths at all. It's just put some dots on a paper and connect those dots with lines. That's it. So what might make something not a network? So if I just use my sketchpad here, you can always access the sketchpad from in the workbook. Here we are, I got some dots. I'm just gonna throw some shapes out there. There are some dots, and I'm gonna connect them with lines. I connect that dot to that dot. I connect that dot to that dot. Okay, that's a network. Oh, I'm gonna connect that dot to that dot, still a network. I'm gonna connect this dot to this dot, still a network. What are these networks for? Don't worry, we'll talk about that later. Right now, we're just dots. We're just dots, and we're just putting edges between those dots, just like that. There we go, we got a network. So let's think about these. Why might some of these not be a network? Well, let's see if we've violated any of those rules. Dots and then lines connecting those dots. So first of all, I noticed this one on the top here. This one, see how you've got a line here that doesn't really go anywhere? It was dots and lines connecting those dots. That is not a line connecting dots. That's just a line that stops in the middle of nowhere. So B, no, B is not a network. The lines have got to connect the dots. This one looks fine. I've got dots and I've got lines connecting those dots. That's cool. This one here, I've got dots and lines connecting those dots. What about this one here? There's one that goes around like this. That one's still okay. You can connect a dot to itself, and that's all right. A dot connecting back to itself, no problem. But this one, you see this little spot here? I never branched my lines. There's a little, like a T junction there. This here is going to be a big problem for us. It's dots and lines connecting straight from one dot to the next. So, because of the problem with this point here and the problem with these guys over here, A and B are not valid networks. But this one and this one, they are both valid because they're just some dots and then some lines connecting dots together. And when I click submit, nice work. Question 1 completed. 90 mastery left. I could keep going. I could keep charging this bar up all the way to 100, but instead I'm going to go back. Now notice, haha, little green line there. So when you load up your own textbook on the topics page, check to see how much of networks you've mastered. If you can charge all of these bars up to 100, then you will have mastered the topic and you will have seen all the different things that you're going to need before your final exam. You'll need to do some more practice closer to the time, of course, but if you're spending a lot of time working on your own, this is a great way to make sure that you're always working on stuff that's relevant and that you're not being given questions you already know how to do. Okay, but I'm going to spend most of my time looking around in the textbook instead of the topics page. I'm just going to go across to the textbook and show you what the difference is. So first of all, notice how I've got Maths Standard 11 selected in my textbook. That was because I just finished a class with the Year 11s. I'm going to select the Year 12 textbook instead. You'll have to excuse me. I have a lot of textbooks. It comes with the territory. And let me find it. It'll be a lot easier for you to find the textbook. New South Wales Maths Standard 2, Year 12. That's the one I want. And I'm going to open up networks. So what's the difference? I'll just add the topics page. This section of the textbook is more for reference. Topics, you charge up your bars, you do your progress, you're mastering things. This section is way better if you want to do particular questions and see how the working out is done. So for example, where's the one that I just did? This one. Which of the following are valid networks? Here's that question again, except this time with slightly different answers. Notice that we've got that triple point again. But if I want, in this area, I can just click on Reveal Solution. And it's just going to tell me the answer and the working out for that question. Now, of course, you're not going to get any mastery for doing this. But it's a good place to refer to questions and brush up on any skills and see the kinds of questions that you might be looking at if you go through the topics page. So it's more useful for me when I'm presenting the material to be looking through textbooks. But I think that when you're doing work on your own, topics is way better because you always get credit for the work that you do in the topics page. Okay. So let's go over to the lesson. Let's say you know nothing about networks. Apparently they're dots with lines connecting them. Okay, what else? Here we are, we have these dots. The proper name for a dot is a vertex, and the name for an edge joining the vertices together is called an edge. And you can see here in the lesson, these are the two cases that we were ruling out in the previous section. We can't have things like this, we can't have things like this, but here are a bunch of different networks. Here we've got some dots and some lines connecting them together. Same here, hold on. Those have got arrowheads. Okay, we'll keep that in mind. These ones have got numbers on their edges. These ones have got letters or labels for the vertices. So sometimes edges can have numbers and sometimes vertices can have some sort of a label. But the study of networks is just playing around with these things. In my opinion, it is definitely the most fun topic out of Standard 2 in Year 12. As I mentioned, some of them have arrows on them. So a shark eats fish, the arrow is definitely that way. I mean, maybe if a shark dies and whatever. In general, sharks eat fish, not the other way around. So it's a directional relationship. Whereas France and Spain share a border. France borders Spain, Spain borders France. There's no need to put arrows on that. So sometimes they have arrows, sometimes they don't. So far, so good. We can also move around a network in various ways, and I'm going to do a question in just a moment. If you start at any vertex, let's say A, you can go A, B, A, E, F, D, E. It's just walking around a network, starting at a vertex, moving to another vertex, going along an edge. I couldn't go A to C. That wouldn't be allowed because there's no edge connecting those two things together. What do these two walks have in common that this one doesn't? So I'll just go through. This one starts you off at D, and then you can go D, G, C, F, E, A. This one starts and ends at B, B, C, F, D, E, A, B. Both of these only use each vertex once. The first kind, where you're just walking around, it's called a walk. But for reasons that we'll get to a little bit later, if you don't repeat a vertex, it's called a path. Sometimes that can be a really important thing. So the best thing to do when you're getting started with networks is to just draw some things that look like this, and then start coloring them in, drawing in your walks and your paths, and you can get started. So here, let's jump into the question set. We go to the top and click on questions. And I want to do a question on walks and paths just to solidify what we've learned. So remember, in the textbook section, I can go through and I can pick whatever question I want to do. But if I pick the question through the textbook, I'm not going to get any credit for it in Mathspace. We've got to go over to topics and do the practice to make that work. Okay, so a couple of different questions here. Let's try this one. This says enter a path from B to X. So paths means I can't use the same letter twice. So how can I get from B to X without repeating any letters? Well, I think there's two ways. B, Y, Q, X. I could go around this way, or I could go around this way. B, H, W, X. What's the right answer? Well, either one is going to get you the tick here. So B, Y, Q, X. Correct. If you'd enter the other one, you've got the other one. The fact that it's a path just means that we can't repeat ourselves. So we can't go B, Y, B, Y, B, H, W, X. That's a valid walk because you can walk around that way, but it's not a path. You can't repeat vertices if you're doing a path. Okay, let's try this one. Enter a path that starts at Q and visits 4 vertices, including P. Okay, let's get our sketch pad out for this one. Starts at Q and visits 4 vertices, including P. So Q, and then 3 more, and one of them has to be P. There are plenty of options for us to choose from. Q, R, P, T. Let's try that. Q, R, P, T. Great. All right. So far, what do we know? What have we learned? So networks are dots, and you put lines between them, and you can do walks and paths around them. What else is special? I'm actually going to start off by talking about what's not special about networks. Where the dots actually aren't that important. So I'm now looking at the lesson for 9.02. What you see on the screen here is a picture of Australia, and each of the capital cities are marked with a dot. What I'm going to do is I'm going to draw a line, an edge connecting these vertices if the states have, so if there are roads connecting them together. So Sydney and Brisbane, there's a road that goes from Sydney to Brisbane. There's a road that goes from Sydney to Canberra, from Canberra to Melbourne, from Melbourne straight to Sydney, not via Canberra. Hobart, there's just a road that goes back to Hobart. Melbourne goes to Adelaide. Adelaide goes to Port Augusta. Port Augusta goes to Perth, and so on. So these are all the roads connecting those cities together. Now that I've represented the roads as edges on this map, I can get rid of the map. I don't need the map anymore. And you can move the dots around and change the shape of the edges, because all we really care about is that Perth and Katherine are connected. We don't particularly care how they're connected. So this picture here looks very different from this picture here. It looks way different from the map of Australia all the way back up the top there. But we can move vertices and edges around to make sure that all we're representing is the information that we care about. If all we're asking is Sydney and Brisbane connected by a road? Then I can look at this and say yes. I could say, if I wanted to drive from Sydney to Perth, how many different ways could I get there? If I didn't want to repeat myself, I didn't want to go back, how many paths are there from Sydney to Perth? Then this diagram is just as useful as this diagram. I can say, well, I could go Sydney, Brisbane, 3 ways, Catherine, Perth, Sydney, Brisbane, 3 ways, Port Augusta, Perth, Sydney, Canberra, Melbourne, Adelaide, Port Augusta, Perth, and so on. I don't have to be looking at this map if I've represented everything I care about like this. So that's why the #1 place you're going to see networks is on rail maps. Now, if I just open up, let me find Sydney rail map. Now, anyone who's been on a Sydney train knows and loves this map. Now, looking at this, it seems to suggest that Cheltenham, Beecroft, Pennant Hills, Thornley, Normanhurst, they're all the same distance away, and they're not the same distance away. The thing that we care about are the stops, not actually how far away these stations are. So the distance between Burwood, Croydon, and Ashfield is less than the difference between Mount Ku-ring-gai and Berowra. Like, this is a lot further apart than these, but this is only representing the connections. So on this lesson, 9.02, if you scroll down long enough, you'll find these applets. And these are just going to let you play around with some networks. Every single way that I can arrange these dots, this is all the same network. I'm not changing anything about it by moving these vertices around, because the most important thing is how these dots are connected to each other. Same with this one. I can move these dots around, and because the relationship between the dots doesn't change, all of these networks are the same. So as we do more work in networks, we're going to be moving things around. But just remember, it's just dots and lines connecting each other. Exactly where the lines are in space and exactly how long the edges are doesn't really matter. If it does, we're going to use numbers or letters or some other thing to go on top. So we're going to now turn to a topic which is called a minimal spanning tree. We're just going to jump right into this one. So I think there's a good example down in the second part. Okay. Here we have a map of cities in, I believe that this is in Victoria, and they've got some great names. So I'm going to just turn my annotation on. So what I've got here, each of these represent a town in Victoria somewhere, and these numbers on the edge represent the distances. Now remember what I said about the actual position of the dots not being important. That's why this 38 is shorter than this 35. The number is what's important, not the actual length here. What the numbers in this diagram represent are the distance between each of the towns. So what's the distance between Sea Lake and Hopeton? It's 50. What's the distance between Beulah and Warracknabeal, 34. What about Donald to Charlton? It's 26. What I want to do here is I want to find if I have to connect all of these cities together, let's say it's for NBN, how do I actually connect it together, each city together, with the smallest amount of distance? That's why it's called a minimal spanning tree. Why it's called a tree, we'll get to in a second. But I want to find the smallest distance required to connect everything together. Okay. So I'm just going to select a better color here. There we go. All right. How am I going to find it? Well, you may have seen a number of different ways to do this, and I'm going to do it my favorite way. You can use this way too, if you like. And this is how it goes. If you ever are confronted with any of these minimal spanning tree problems, all we're going to do is we're going to start counting at 1, and we're going to count up until we're finished. Okay, 1, 2, 3. Okay, a little bit boring. What's the lowest number across this network? It's 18. It's right here. Cool. So 18 is the lowest number. We're keeping it. And by taking 18, I've now connected Hopetoun and Beulah together. So after 18, what's next? 19, 20, 21, 22, 23, 24, 25, 26, 26. There's one with 26 here. Cool. We got this one. And there's another 26 over here as well. Okay. We're just going to keep on doing this. 26, 27, 28, 29, 30, 31, 31. Cool. No other 31s. Okay, 32, 33, 34. Got one. 34. Oh, wait. I missed one. Let me just undo that for a second. There is another 31. This one over here. But I've already connected Rainbow and Hopetoun together. Rainbow and Hopetoun can go via Beulah. So I actually don't need this 31. So let's go back to counting up. 31, 32, 33, 34. Cool, there's a 34, taking it. 35, yes, 35, cool. Just double checking I haven't missed any. 36, 37, 38. There's a whole bunch of 38s all coming out of the middle one. Which ones do I pick? It doesn't matter, just pick them one at a time. So what's our favorite 38? Let's go with this 38. Cool. Now, this 38, the one over here on the right, I don't need to use it because I've already connected Birchip and Demosa together. They'd have to go around the long way, but I don't need this one anymore. But this 38, Beulah and Birchip, they're not connected right now. So I am going to take this one as well. So I take this one, and I'm not going to be using this one. Okay, 38. Now, notice that everything's connected now. I've connected every single town together except for Sea Lake. I just need to connect it. I can keep counting up if I want to, from 38, 39, 40, blah, blah, blah. But all I really need to do now is connect Sea Lake to the rest with the shortest distance possible, which in this case happens to be 50. So now what I've done is I've connected every single dot together in the one network. And if I was to add up all of these numbers, let me just change color here. If someone said, how much cabling are we going to need? Well, I can just add up the numbers on each of these edges, like so. If I add up all those numbers, that'll tell me how much cabling I need. But by doing the procedure I just went through, I'm guaranteed to have the smallest amount of cabling required to connect everything all together. This particular algorithm is called Kruskal's algorithm. I like it. I think it's pretty cool. There's another one, which is called Prim's algorithm. If you learnt how to do this differently, then try Kruskal's algorithm. If you've already tried Kruskal's algorithm, go into 9.06 and try out Prim's algorithm. They're both easy and once you get used to them, once you've done a couple of practice runs, and it will mean that you can answer any and all questions on minimal spanning trees. Okay, so I'm going to clear these drawings and zoom out again. So if you look through the lesson, you'll see exactly what I was just talking about is all laid out there as well. It's got a slightly different spanning tree because picked this 38 rather than that 38, but the same result. Now, remember I did say earlier, I was like, oh, I'll tell you why it's a tree later. The reason why we call it a tree is because it has a very important property. Trees in networks look like this. So I'm going to draw a tree on the screen. Here's a tree. I'm just drawing a tree. Yes, this is real mathematics. It is very serious. There we go. So what is it that makes this thing a tree and this thing down here? What makes this a tree? Well, the important thing is that there's only one way to get from any dot to any other dot. If I start at Sea Lake, how can I get to Bort? Well, there's only one way. Sea Lake, Hopeton, Beulah, Birchip, Demosa, Charlton, Bort. That's the only way. If I were to try and go this network up the top here, that's not a tree, because there's heaps of ways to get from Sea Lake to Bort. Same with this tree. Pick any dot on this tree, and there's only one way to get to any other dot. And it comes up all the time in what are called minimization problems. Someone wants to use the least amount of cable in order to do a broadband network. They want to do something else that is as small as possible or as least as possible. We're going to take a look at some examples in the questions. So let's take a look at the questions. Questions. Some of these are super easy. We're going to go with a slightly harder one. Let's take a look. Okay, this one looks good. Let's do this one. And I'm actually going to do a little bit of a, so what's the number? This is like a little privileges of working for Mathspace. I'm going to load this up in a different place. So if you load it up in Mathspace, it's going to look like this as a multiple choice question. But I'm actually going to load it up in this environment, which gives me a slightly different pen. I'll zoom in. So what kind of a thing have we got going on? Underground service tunnels are required to connect electrical substations together. The given network displays the underground distance between substations. The project is on a limited budget, so they have to design a connection that requires the shortest overall tunnel length. So underground service tunnels, it's a big deal to dig tunnels underground. They want to do as little of this as possible. So how are they going to do it? Well, remember, to do this kind of problem, you just got to count up, start at 1 and count your way up. And whenever you hit something that has the number, either add that edge in or knock that edge out. Okay, so let's start with the first number, 1. No 1s, no 2s, no 3s, no 4s, no 5s, no 6s, no 7s. Hello, 8. Yes, I will have you. Okay, no other 8s. Okay, cool. 9. Nice. Okay. So now we've connected F and G and J and I with service tunnels. No other 9s? Okay. 10. 10. Found one. Cool. Now F and G and H are all connected. J and I are connected. 10. No other 10s. Let's go 11. 11. Here we go. There's one 11 and there's one 11. 12, no 12s. 13s, no 13s. 14s, yep, 14, 14. 15, yes, there is a 15, but J and F are already connected. These are the people who dig the tunnels, not the people who have to use the tunnels. So if you had to get from J to F, you'd have to go all the way around this way. So J through to F, but you can get there. So if someone says, please make J to F, you're like, no, limited budget. It's gotta be, you gotta go around. So I'm not gonna pick up 15. This 15, however, that one looks good. Right now, there's no way to get from A to D, so I'll include it. Now I've almost connected everything together. I've just got to connect B to something and I've got to connect this bottom bit to the top bit. But remember, all we're doing is we're counting up from the bottom. So 15, 16. Yes, there's a 16. I'll take it. There is another 16, but we're going to tell these people the same thing we told the last people. You're just going to have to go the long way. Limited budget. All right. Okay, so 16's done. 17. 17, yes, and B hasn't connected to anything yet. Okay. And what have we got? We've got every dot connected to every other dot, and we are using the least amount of digging that we need to dig, because there's exactly one way to get from any vertex to any other vertex. Okay, so that's this problem. I've just seen a question come up in the Q&A. Here we go. So someone's asking for what topics are coming up in future classes. Now, if you go to, how about I go to mathspace.co/academy. Well, cool. Teething issues there. Normally, if you go to mathspace.co/academy, there will be a schedule. Everything for term 2 is planned for both year 11 and year 12 standard. I will find it myself in my other screen. And I apologize, there's some teething issues, obviously, but this is the manual one. The Mathspace Academy homepage should, once it gets back up, it's crashed because we're so popular. Once it comes up, you'll be able to see all of the upcoming subjects, but once this loads up, you'll be able to see what I'm planning on covering throughout the rest of term 2. Okay, that's year 7, year 8, year 9, year 10, year 11. So for year 11, we're doing budgeting, then probability, linear relationships, measurement, and representing data. And for year 12, after networks, throughout the holidays, if you're super keen to come along and do some trig overview with me on Thursdays, then you can join me for trig over the next 2 weeks. And then after that, we're doing some bivariate data analysis, which is really cool to say. You can say, hey, what are you studying? I'm studying bivariate data analysis. Super cool. And then we've got nonlinear relationships, finance review, and annuities to close out the term. So apologies for the potato quality schedule here. It's going to look all nice on the website once that comes back up. And if this is relevant to you or your classes, then send them along. Okay. All right. So that was, that has been minimum spanning trees. There are a bunch of questions in Mathspace. So if you think you're ready to do the whole counting from 1 up to the top number and just don't make loops, I reckon you can go through and smash all the way through to 9.06, master every single subtopic, and each of these have some interesting ideas that are going to help you whenever you come up with networks. Now, because of time constraints, I'm not going to be talking about this section, the planning activities with dependencies. This would probably take a whole hour just to go through just the planning with dependencies. It's kind of the most advanced part of the networks topic. It's actually really cool. And if you have ever thought to yourself, when am I ever going to use this maths? Well, every single event manager that I've ever met does this kind of mathematics. They may not know that it's mathematics, but this is what they're doing. Making sure if you ever have a project where you're thinking, one day I want to lead a team of people doing a thing, whatever that is, you're going to be doing the kinds of things that's discussed in this area, and it's actually really fun. But I will not be able to cover it in the 10 minutes I have remaining. So instead, if you are particularly keen to see me go through it, because as I said, over the next 2 weeks, I'm going to be overviewing trigonometry. And in general, I'm going to be trying to cover 2 to 3 subtopics per week maximum. Today was meant to just be a welcome and show you around. And networks is my favorite, so I picked networks. So I'm actually going to move instead into something that's called flow networks. What is a flow network? I just want to get you started here. So first of all, there's a video if you go into the lesson. If you watch this video, you may recognize the voice. It's mine. This video will walk you through the basics of what you're going to need to know to get across flow networks, what they are, and how to do the things that we're going to need to do. And so if you watch this video, you'll be ready to master 9.11 or whatever the equivalent one is for you in your state. But I am going to take you through the lesson just to give you a bit of an intro, just in case the video doesn't quite service what you're looking for. So let's start off by taking a look at this network and seeing what it represents. So we'll take a moment. So I've got, what have I got? I've got factory, warehouse, New York, Hong Kong, Milan. Okay, I can see what maybe this is doing. We've got a factory. It's got an arrow because things go from the factory to the warehouse, not the other way around. Things are going from factory to warehouse, 120. Things are going from the warehouse to these cities. And what are they? It says up here, the number of shirts that can be shipped from one location to another in a month. So the factory can ship 120 shirts to the warehouse. And the warehouse can ship 200 shirts per month to New York, 50 to Hong Kong, and 100 to Milan. So the warehouse can ship out a lot faster than the factory can ship in, right? The factory can send 120 each month, and then there's 200, but it's never going to get 200 coming from the warehouse through to New York. So we call this number the inflow capacity. No more than 100 shirts are coming from the factory into the warehouse. And the outflow capacity here is 350. The warehouse can ship 350 shirts, but instead they're just saying, come on, factory, send more, send more. So this situation, as you can imagine, is embedded in everyday life. Not always factories and warehouses, but generally speaking, someone wants more of a thing than someone else can provide. So the inflow capacity and the outflow capacity are both represented here. This is another situation with a flow network. Here we've got the lunch line. How many students can move from the playground to the lunch line per minute? Well, maybe that's like the size of the door. Maybe the door is a little bit bigger from the oval to the lunch line, but playground to lunch line is 8, oval to the lunch line is 10. So all up, 18 students can join the line in 1 minute, 8 coming from the playground and 10 coming from the oval. But everyone's going to get all bunched up here behind the lunch line. The lunch line can only cater to 5 people per minute. So it doesn't matter, like these people are just going to be backing up and backing up and backing up. And only 5 people per minute are going through, getting their lunch and going to the tables. So do you see how these two situations are kind of the opposite of each other? In the first case, we had the factory being really slowly trickling the shirts in the warehouse saying, come on, I've got 200 customers in New York, I want to ship them faster, but there's not enough shirts coming in from this way. Whereas this is kind of the opposite problem. You've got all of the students streaming in at lunchtime, backing all the way up, and only 5 can trickle through. So this is called a flow problem. Now, students and t-shirts don't flow in the way that liquid does, but there's a unifying principle linking all of this together in the language of networks. And what kind of a problem we're going to be solving in flow networks is how many can go from one place to another when it's slightly larger and more complicated. So here I have a network, and I'm just going to zoom in so I can make better annotations in just a second. This is a far more complicated network than the one I was just talking about. This here is the maximum number of flights that can go from one airport to another. Airport SFO, SEA, LAS, JFK, DFW, ATL. If you're familiar with airline codes, you might be able to guess where this is from. But how many flights go if all of these flights left first thing in the morning and then went through like this? How many flights make it all the way through to Atlanta in a single day? You got 8 planes coming out of SFO going to SEA, and you got 23 coming out of SFO and going into LAS. After that, what happens? How many of these planes that leave SFO, how many make it to ATL by the end? So it's kind of like a puzzle, but this kind of thing, if you're an air traffic controller, this is going to be a very important puzzle for you. In fact, you're going to get paid a lot of money to solve this kind of puzzle. And of course, this is airports, but you can use your imagination to think about all sorts of places where this kind of thing might happen. So what's going on here? How do I approach this problem? So I'm just going to get my annotation out, and we're going to start with a little bit of terminology. First of all, there's something special about this vertex and about this vertex. each of these vertices in the middle, notice how they have arrows coming in and arrows coming out. LAS has got 3 arrows coming in and 1 arrow coming out. DFW, 2 in, 1 out. Same here. But this one has only arrows coming out. We call this one the source. It sounds cool, and it's the source, in this instance, of planes, source of planes. And this one here, it only has arrows coming in. You can think of it like the finish line. This is the sink. Okay, so sink, source and sink. Sink, you can think of it like a drain, like a sink in a drain. That's where all the things eventually flow into. Okay. Now, as you may have already guessed from the top here, we're going to be using the max flow min cut theorem. Now, in my opinion, this is the best named theorem in all of maths. It's not Pythagoras. Each of us had to learn how to spell Pythagoras. Some of us still get it wrong. Like, what does that even mean? This one tells you that the max flow is the min cut. Cool. Okay, max flow, we've been talking about flow. What's a cut? All right. To do a cut, I'm just going to get a new color out here. To do a cut, I'm just going to, oh, blue, I've already got blue. Let's go pink. Pink's a nice color. All I'm going to do to make a cut in this network is I'm going to draw a line that separates the source from the sink. So here we go. Here's one. There's a line. On the left is the source. On the right is the sink. What I'm going to do is I'm going to count up all of the numbers where the arrow is crossing from the source to the sink. So here and here. This arrow here is going backwards. I'm not going to count that. I'll explain why in just a second. So I've got 6 and 20. This cut that I just drew, I give it the value of 26. What this number means is, in any day, at most 26 aeroplanes are going to cross from this side to this side. That's why we don't count the one going back this way. We're only counting the ones going this way. So each day, 20 can go this way and 6 can go this way. At most, 26 are going to be flowing from this side to that side. So I'm going to keep the number 26. I'm going to get my eraser out so that I can make a few more. So I've got this cut here, 26. Now, draw. I'm pick a new color. Let's go green. Yes. Remember the name of the theorem. Min cut. I'm trying to find the maximum number of flights. That's the max flow. So I'm looking for the minimum cut. So what I do next is I draw a new cut and I see if I get a number that's lower than 26. So let's try, is there a way to do it? Let's try this one. It's probably wrong, but we'll do this one. There's a new cut. Notice that once again, I've separated the source on the left from the sink on the right. So I can say how many planes can cross from the left-hand side of the green line to the right-hand side of the green line. So 8 is crossing from the left to the right, so I'm going to count it. 5 crossing wrong way, don't care. 4 crossing wrong way, don't care. 20, yep, I'll take you. 28, oh, but 28's not less than 26. It's the minimum cut. So yeah, 28's no good. We're going to see if we can cut it any other way. So we can cut it this way. If we cut it this way, let's try and add them up. Purple, cool. Okay. So this one has got a 6 here and a 5 here and a 23. That's definitely no good. That's way too much. So this one here looks like 26 as well. If I do this one, I get the 7 and the 19, but I don't get the 4. So let's just keep checking, see if there's any other ones that I'm missing. I think 26 looks pretty good. So try to cut. We'll find out whether or not I'm right. Let me just turn the annotations off. Boop. Oh, and I'll clear them as well. Annotate, clear. See if I missed any. Clear all drawings. Oh. And get rid of annotate. There we go. So here's just an example in the lesson. Again, all of these lessons are available to you and you can read them through at your leisure. And 26, the one I drew right at the beginning, was the best one. There are some other examples and you can try it out. But isn't that, it's pretty cool, right? We start by going, okay, how many planes go from one airport to the next? And we just define each of these. And by playing that game of just drawing a cut, we can now figure out what the total flow throughout the whole network is. Now, as I said, this is air traffic control, but this is also everything from the way that we design our roads and our streets to the way that we route internet traffic around the world, to the way that we allocate seats at gala dinners. There's all sorts of things that end up being modeled as a flow problem. There is a video, as I said at the top here, and what I've described to you right now is all you really need to know to master the flow networks part. Maybe later this year, I will take a look at doing this, the forward and backward scanning and critical path analysis, which I think is the trickiest, but definitely the most powerful part of networks. If you're feeling particularly adventurous and have nothing else to do, I mean, all of us are stuck at home, thanks Corona, and jump into the topics page and try some of these out for yourself. Try the lesson, try some of the questions, and see if you can get all of those bars up to green. Or try doing similarly with whatever other Mathspace you're doing. So I am, okay, 11:59:57. I didn't leave much time at the end. But if you do have anything that you'd like to share, leave a message either in the chat or the Q&A. I'll hang around for a few minutes, but otherwise I will see, we are back on next Thursday. So most of Australia is going to be on school holidays, but I know Victorian students are back at school just after Easter. So next Thursday and the Thursday after, we're going to be doing a review of trigonometry, and then we'll move into, as I said, bivariate data analysis the week after. So there hasn't been any questions or chat. If you think of something, then let your teacher know and they can get in touch with us here at Mathspace. Have a great Easter, and I'll see everyone after the Easter break.